Welcome, ladies and gentlemen, to this presentation of the embedded development cycle at ETAS. First, please let me introduce myself. My name is Martin Keil and I'm the product owner of this project. I have 18 plus years of experience within automotive software development at Bosch and at ETAS. I've structured this presentation into three main parts. First, we'll take a look into the overview and pain points. Second, we'll go into the architecture and big picture of the toolchain. And last but not least, I will give you some live demonstration of some selected use cases we have implemented so far. To handle complexity, cost, quality, and time to market, changes are necessary. To follow the new software development methodologies, we would like to enable our customers to have high iterative steps, small, powerful, and purposeful teams, and data and AI-driven development. This is implemented by having some CI/CD-based toolchain in the background. ETAS provides cloud-based workflow with bundles third-party and ETAS tools in some integrated toolchain, adding workflow UI and KPI dashboards. We want to provide you virtual desktop use cases, as we will see in just some minutes, as well as CI, CD, and CT-based automation pipelines. Everything can be installed in the cloud, either on our side or on your own subscription-based. There's a seamless automotive embedded software development workflow introducing AUTOSAR, as well as topics like ASPICE, variant management systems, and certifications. The offer is based in three main parts, as you see in the slide. We have the coding aspects, the build aspects, and the testing solutions. Some main pain points we have figured out together with our customers so far, you can see on this slide. First, the aspect of speed. So this means the reduction of development time or time to market, coming from days going into some hours only. Next big point is the maintenance. So what we would like to do is take away all the updates, IT infrastructure, and so on, to make it possible for you to focus on your daily business and on the outcome you're looking the most. Certifications and processes should of course be part of some supplied toolchain. Onboarding for new developers is a crucial part to come up with a highly trained and skilled team. Collaboration should be possible within OEMs and tiers. Virtualization is necessary to scale up testing cycles, as we will see in a model simulator as one example in some minutes. And of course, variant handling is a crucial part. Some of these pain points we figured out are the ones we started with and already implemented in some toolchain to be presented to you in some minutes. Having some overview about the embedded cloud toolchain, we see that we have two main parts. One is the virtual desktop solution and one is the automation CI, CD, CT pipelines. Everything is covered within the long-term archivement, and of course we have underlying structures including security and baselines. The main parts to be covered are, as mentioned, the virtual desktop, then configuration and code generation, for example using MATLAB Simulink or using ETAS ASCII. We have the software component integration part, artifactual build, system integration and configuration, and then either the execution on a local test environment or scenario generation and scaled execution, as well as analytics for a model simulator in the cloud. Underlying, as mentioned, we have version variant management as well as a collaboration platform. And today we will focus on the automation part of that aspect. In the next step, I would like to give you some overview about the architecture and big picture of the toolchain. As already mentioned in the last slide, we can see two of our main use cases supported. On the one hand side, we have a virtual desktop scenario. On the other hand side, a CI/CD CT-based build automation. Both of them are combined by some repository where the artifacts are stored. The underlying infrastructure contains of two main parts. First, we have the image factory, which is generating the images used in that infrastructure. And second, we have the build actions, which is the action items to be used in the build automation steps, like a Jenkins pipeline. Both of them need to work together so that the tool you're using for the automation is already installed in the image you're using, and vice versa. For the tool you would like to use, you have the best approach to easily configure your pipeline to your needs. Below both of that scenarios, there's of course a secured platform and infrastructure as code to have some reproducible approach to create your infrastructure. The main use cases from user point of view. First, the user logs into some virtual desktop, which is provided by infrastructure as code, and would like to edit some model. In this case, we just take some MATLAB simulating scenario. So the model is checked out from the repository or the sync the changes, and the user can edit the model online. Once the user is finished, he syncs back the model into the repository. Because of that change, an automated build is started by this change request, and it runs a pipeline. The pipeline can be defined by your use case. It really depends on what you would like to do, and we have a wide array of already pre-implemented functionalities to be used. At the end, log files, build results, and so on are stored in an Artifactory, and the build results are put back to the developer via mail or notification by MS Teams, for example. The images are provided as well as for the virtual desktop, as well as for the build automation. So how images are created? We're coming from the very left-hand side, where the tool setup is available in some versioned Artifactory. So this means the tool setup files like ASCII, MATLAB, eHandbook, and so on. In addition to that tool setup, we need the installation scripts, which also, of course, are versioned. So there's a one-by-one relationship between the tool, or even the tool version, and the installation script. Third, we have the image configuration, which means we define which tools or versions do we want to have in our created image. And here the users can choose. This image configuration is then put into some building process, which is called in-house the image factory, and images or Docker containers are generated by that automated process. And these generated images are then stored in some, for example, Azure image gallery or some Docker registry, and can be used in the next steps using pipelines. One example of such a build pipeline you can see on this slide. We have taken some MATLAB model here as an example, as an input to this pipeline. By the change of that model, a service hook triggers Jenkins on the left-hand side to start a virtual machine, and also then trigger a pipeline which is pre-configured by the user to do exactly what you need to do. Within user responsibility, of course, are also the test cases, which should be used for the smoke and SIL testing integration steps. So by the change of the MATLAB model, pipeline is triggered. First step is here we have a build action to generate the MATLAB code out of that model. This code is then integrated into some VECU build step. It's checked if the generation process was successful. Then we do the integration into a software in the loop system, running some basic smoke test to check if the integration was successfully on a generic level before we start a more detailed testing of that integrated part. Once this is done, no matter if successful or not, user will be informed by continuous reporting, and the files are pushed to some repository. So, to not only show you slides, but also give you some live demo, let's continue with the next part. To give you some impression on our toolchain, I would like to guide you through one of our demonstration use cases. First, I would like to log in to some virtual desktop environment. I'm using a demonstration user, as we're currently working on the single sign-on implementation. In the virtual desktop, we have some installations for MATLAB Simulink, where I've already loaded some model, as well as the Git connection. Here we are using Microsoft Visual Studio Code for that. In the model, I will just do some update of any value to create some change request, and I will save it. Of course, in the real world scenario, you would do much more implementations or more complex implementations on that. Here in the Git, we see that there's a change to the model. So we stage it, giving some meaningful name, and sync the changes to the repository. In that case, we are done with our work, and we switch over to the next step. In our repository, we see that the demo 1234 we just did now is already there, and so the pipeline is automatically triggered by using a service hook. The MATLAB code generation started, we build, and FMU verification and integration will be done. To not waste some time, I will give you that overview via the slides in details. So for the pipeline we have just seen in a slide before, we have the equivalent steps in Jenkins, and we have a one-by-one mapping for each of that steps. What does the pipeline do in detail? So first we do the checkout, preparing the license manager and doing the MATLAB source code generation. Next we're doing a generation of an FMU using the VSU build toolkit. Next we do the verification of that generated FMU. If this was successful, then we're going to the next step and integrate this into some coding project together with some plant models, electrical layers, and so on. We are running some smoke tests just to make sure that the implementation and the integration was done in a basic level, which is ready for testing. And we continue with the continuous testing approach using Robot Framework as one of the available testing frameworks. Last but not least, we will generate some report for the users as well as some optional Teams channel notification. Next, we will continue with the model simulator. Before we continue, I would like to show you some of the reports created by the continuous testing. Therefore, we'll take a look into some of the already generated log information. As you see, the building blocks create different output artifacts, like for example, the FMU generated by the VSU build step, integration parameter, integration artifacts, and for us here, the continuous testing report. There's a log file generated, and we see that here we have the FMU check test case, which contains a number of keyword-based tests, and in that case, everything was done successfully. To speed up the testing cycle even further, I would like to give you a brief introduction to the model simulator service at ETAS. Coming from a traditional vehicle testing scenario, users are limited typically by the availability of a car. To remove that bottleneck, hardware-in-the-loop testing was introduced. Hardware-in-the-loop also typically increases the number of tests done per day. Bringing that scenario one step further and removing the hardware dependency, software in the loop was the next logical step to implement. Here, the users can use their own PC as a testing environment and speed up the number of tests per day. Bringing even that approach to the next level, ETAS introduced the model simulator to do that calculation in a scaling scenario in the cloud. We introduced the model simulator as an additional building block into our predefined pipeline building steps. And with that, you can easily use the simulation services from ETAS to use the model simulator in your pipelines. As you see, the pipeline looks quite familiar with the one we have just seen using the MATLAB Simulink use case. Here, for the ease of purpose, we are using some already pre-existing source code model and do not generate it via MATLAB. The rest is exactly the same. We're using the same build actions in a reusable way as before, but we removed the local building step for the continuous testing and replaced it with the model simulator build step. This does a cloud simulation in the simulation cluster and provides the same reports to the user as before. Having that in the UI of Model Simulator, you see that we have run some speed controller use case, but here we have done it in a highly parallel way, so not blocking the simulation device locally all the time, but we transfer it into the cloud and it's running in a parallel way, easy, secure, and fast. If you have any questions regarding the topics mentioned, please feel free to contact me, my product manager Markus Behle, or any sales team at ETAS to give you some in-detailed presentation of the topics you are interested in. I would like to thank you for the interest in the embedded development cycle and wish you a nice day.